Our next speaker is Pieter Abbeel from UC Berkeley, OpenAI, and Gradescope. And we will run a little bit into the lunch break, but I hope you all agree that it's better to have these interesting discussions than to rush the invited speakers or stop them. So please welcome Pieter Abbeel.
All right, so outline of what I'm going to talk about. First, a little bit of deep learning Kool-Aid, overview of successes from past few years. Then the direction I've been pushing in my group, which is deep reinforcement learning. And then I'll look at some directions that I think are very important to address in the near future. So probably the biggest successes in deep learning have come first, at least in computer vision, where until 2012 it was common practice to engineer a feature representation like Hog or Sift or Daisy or the next one in line, feed that representation into a support vector machine that's trained to recognize what's in an image and get mediocre performance. And that got eclipsed completely in 2012 by deep learning, the result from Jeff Hinton's group. The data set they worked with was ImageNet. And when I say eclipsed, there's a competition, and this is held every year. Horizontal axis is time, vertical axis is error rate, lower is better. And so what you see here is traditional computer vision approaches coming at about 30% error rate and slowly inching down. But then Jeff Hinton's group came in right here, leaped forward. At that point, almost everybody switched except for the one blue dot there, one stronghold still in 2013. But everybody else was doing deep learning the next year and the year after. And not only is there a jump forward, but also an acceleration in progress. Same thing happened in speech recognition around the same time, in fact, slightly earlier. And at the time, it was interesting. You could talk with computer vision professors, and some would say, yeah, these neural nets, they might look amazing, but all they're doing is just like recognizing what's in an image. They're not understanding what's in the image. This is just like yet another tool in our toolbox. It's great. We can use this. We have so many other tools, but it only does one thing. It doesn't recognize an image. That's what vision is about. Well, it doesn't understand the image. That's what really vision is about. Then, a little later, another data set comes out, Microsoft COCO data set, which is on image captioning. And sure enough, in 2015, there were 8 papers at the same time, very soon after this data set came out, that were able to show that deep learning can learn to caption some of those images. Again, supervised training, but some example. Bottom left, girl in pink dress is jumping in air. Pretty good. Some are not perfect, of course. Young girl in pink shirt is swinging on a swing. It's not swinging on a swing, but it's close. It's getting some notion of what's going on in that image. Again, people would say, well, it's just generating a caption. There's so many possible captions. Has a lot of things to pick from. It's probably not that precisely knowing what's in the image. Well, somebody built a new data set on visual question answering. This is the visual Q&A challenge, which a lot of computer vision people work on right now. Some examples. Let's look at the third one in the top row. Here there's an image and a question. How many school buses are there? The neural net says 2. That's behind this particular engine. And then the ground truth is 2. It's not always right. Bottom right, for example, what are people sitting under in the back? The neural net says bench. But it's asking about where they're sitting under, and actually the truth is that's sitting under a tent. So this is not a solved problem, but this is inching forward too, and getting a lot closer to actually understanding what's in those images. Still, you might say, well, it's kind of frustrating that we need to generate a new data set for every task. It's a lot of work to label those things, a lot of trickery getting the labels. Well, how about unsupervised learning then? Principle, a much harder problem. The idea is that you are supposed to learn from things that have no labels at all, discovering the structure intrinsic to the data. So one unsupervised problem that you could try to tackle is, can we build a system that learns the manifold of images, can generate images, assign a likelihood to every possible image you present to it, and so forth? Sure enough, that's where a lot of breakthroughs have happened in this past year. There are 3 main lines of work that are achieving state-of-the-art right now. Variational autoencoders, which explicitly model the likelihood of every image you present to it. Generative adversarial networks. They fix some of the prior issues people have had with image generation, where typically you get blurry images. These GANs, what they do is they have a generated network, but also a discriminated network that tries to decide whether the image that it's presented to was generated by a computer or was a real image from the real world. And so if you generate a blurry image, that thing will have a very easy time telling you that's a auto-generated image, not a real image. So you can't generate blurry images anymore once you work in that regime. And then pixel RNN, which essentially goes pixel by pixel, constructing one pixel at a time what an image should look like. What this looks like underneath for the GAN networks, you have a code that's 100 or 1,000 variables, depending on how big a code you want to set up. That's a Gaussian variable. That Gaussian variable then gets fed through a huge neural net that ultimately generates a full image. Here's what the training looks like. So these are some recent results. Initially, it was just noise being generated, because with random parameters, random input, you get random output. But over time, as this GAN is being trained, it starts presenting things that look like images that are in the training set. So let's start again from the beginning here. So initially, this is just noise. But then over time, training will force it to generate images that look like real images. Let's take a look at some final results. So one side here is real images. The other side is generated. If you look carefully, you'll find out which side is generated. Who thinks it's the right side that's generated? OK, so half the people think that. Who thinks it's the left side? I guess half people are abstaining. So indeed, the right side is automatically generated, but it's starting to look at a first glimpse, at least, as something that could be a real image. Then you could also say, well, it's great to generate random images, but does it really understand the structure of those images? And so a little thing we did over this past year is infusing a little bit of structure into the GAN generation network. And what we do is we say we want there to be not just a random Gaussian input vector, but there are a few extra variables. And for those variables, we want there to be high mutual information between what's in those extra variables and what's in the image, meaning that essentially you hope that you're able to infuse some bits of information that are easy to recognize later from the image you generated. Once you do that, again, you need no supervision, no labeled data. You can get things out like this. So let's look at what's going on here. Top left, if we look at the top left row, a row corresponds to one Gaussian vector that was sampled. So there is one Gaussian vector sampled, and then there is one extra variable for which we have mutual information with what's being generated that we're sliding from its lowest to its highest value. As we slide it, we see that that face, which is generated, by the way, changes its pose. But it's the same face, it's just changing its pose. There's a different angle of changing pose for the top right block. If you go from row to row to row, you have a different Gaussian vector. If you go left to right, the slider, that extra variable is being changed. Bottom left is sliding, and then bottom right is whether the face is wider or narrower. You can also get other things which aren't as pronounced but are getting there. Things like on the left, you'd have somebody not having glasses, and by the time you're on the right, they're wearing sunglasses. In the middle, they're wearing glasses that are transparent. Like mine. You can have things where you can have a picture of somebody like me that gets turned effectively into somebody who has hair again. All kind of things as you go from left to right. So a lot of progress in computer vision. In robotics, we have a slightly different problem. You have perceptual inputs, you have some state estimation usually, then some control system, and you want to then maybe tweak that a little bit to get good motor commands out. You can ask the same question. Let's just swap in a big neural net, see if we can learn the whole thing. And maybe we could, because all that's happening in the top paradigm is computation, and a neural net is flexible computational fabric, so maybe with the right amount of data, the right structure of the neural net, it'll actually learn the right thing. You can also isolate some blocks. You can say, let's just look at estimation. There's a lot of progress there, where through end-to-end training, it's possible to improve estimation in things like Kalman filters for tracking. But then also at the bottom right, actually, there's something very interesting happening. This is work by Matt Johnson at Harvard. What's going on there is he's combining a Kalman filter with these variational autoencoders that are able to generate images. And so now you have a Kalman filter where you actually don't feature extract anything from the images you feed in. You actually have a generative model for what the image percepts are going to be. And so there's a full-blown generative model for visual tracking. Once you have estimation, you can also do things with it. Some problems, once you have estimation, they're kind of solved. If you, let's say, all you need to do is kinematic control to solve your problem, once you understand where your robot needs to be, you can build a model for your robot, because it's just your one robot. It's not a lot of effort to build a model for one robot. And you can do things like grasping, if you know how to recognize where the grasps should be. Or you could potentially do, like in a DeepMBC paper, do online estimation of the dynamics of how your knife moves through some things it's cutting to get better control. But personally, what I've been interested in largely is how we can actually solve the entire control loop. Rather than parceling it apart, can we do the whole thing? Can we have a robot that's put in an environment, takes in percepts, somehow processes those, and puts out controls, and this then repeats? There are some challenges compared to supervised learning. The supervision is much sparser. All you get is rewards every now and then. You might be a robot in a maze, you might be busy for a very long time, get 0 reward, and finally when you exit the maze, you get a +1. And now finally you're able to learn something about what you're supposed to be doing. So it's very, very sparse information. So aside from the credit assignment problem, because the information is sparse, there's a stability problem. If you're not careful while you're training your system, you could destroy it during training, which might defeat the purpose. And then there's a problem of exploration, consistently trying to find out what are things that you don't know about yet that you could learn about. Nevertheless, there's a good question there in terms of how can we go all the way from pixels to actions. A good place to start, since data is always helpful, more data is better, is video games. And here you see some snapshots of Atari Games. DeepMind was able to learn a deep net that goes all the way from raw pixels to joystick actions. The difference between this and AlexNet is essentially that in AlexNet, which was Jeff Hinton's and collaborators' breakthrough for visual recognition, is that instead of outputting an activation for cat, dog, horse, car, and so forth, you output an activation for each possible action. Still confident, fully connected layers, and so forth. This is from their Nature paper. Since then, the results have even improved. But what you see here is that on about 2/3 of these Atari games, a single system, the system doesn't change. You use the exact same algorithm for Atari Game 1 as you use for Atari Game 2, and so forth. Single set of hyperparameters, single neural net architecture is able to train for any one of those tasks, and for 2/3 of them, it's able to do as well as human performance. My interest has been in robotic control, so the question is, can we do something similar, positing a neural net that can go from raw inputs to controls? There are some challenges with Q-learning. So Q-learning is what was underneath how the DeepMind Atari Games DeepNet was trained. But the problem is there's an output for every possible action, which is expensive to output, especially if you have continuous actions, high-dimensional spaces. It's impractical to discretize that and work with that. Another challenge with Q-learning is that it's hard to measure progress. It's very difficult to run a Q-learning and see consistent progress, because it's optimizing the surrogate objective of Bellman error, which doesn't always directly tie into what is direct performance improvement. So what we've been looking at, and have had an easier time making progress with, is policy optimization. So here what you say is there's a big neural net, which represents your policy, which goes from perceptual inputs to controls. And as you change the weights in your neural net, well, you can roll out some executions with your neural net, see how well it does compared to what you had before. So at any given time, you can measure whether you're making progress or not. So often, easier to work with. There's some good existing work that tells you how to compute gradients when you do policy optimization. In fact, what you really want is natural gradients. But even when you use the existing natural gradient work, what we found is it's very hard to get good step sizes and learn in a small number of iterations. So we had to add a few things to that. What we did is essentially we looked at policy gradient methods, and we added a trust region. What is this trust region thing here? This thing here is saying that under your current policy, big neural net with parameter vector theta, you have a distribution over trajectories. That's p tau theta. If you change your parameter vector by some small change delta theta, you'll have a new distribution over trajectories. You want that new distribution over trajectories to be close to your previous distribution. Because the first order approximation you're making to your objective will only be accurate as long as that holds true. But if that holds true, then that approximation is accurate. And so this way, you have a good way of measuring where you can trust your approximation. And sometimes you can make very big steps, actually, in parameter space, but they'll have to be small steps in the space of distributions over state action visitations. You can actually do slightly better, and we'll have the details in the paper. Instead of using a first-order approximation, there's a surrogate loss that is possible to define that gives you a second-order approximation that is a bound on the actual performance, and that way you can do even better. Even then, if you look at the standard gradient calculations that would come in here, they're pretty noisy, because they're based on essentially a sum of rewards that you get after the current action. So the gradient looks like this: expectation, which you can compute through averaging, of the derivative of the log probability of the action you took, multiplied with how much reward you get, difference with the value function. What does that mean? If you roll out based on your current policy, if you did better than average, the value function is where you would do an average. That's what it essentially is. If you did better than average, the action you took should increase its probability. If you did worse than average, you should decrease the probability of that action. Turns out you need to be really careful about what you do here in terms of computing the value function. We set up a trust region approach for that too. Big neural net for the policy, another big neural net for the value function. Once you have both of those, you can actually get really good results. So here, what we're looking at is learning locomotion from scratch. So this system has about 100,000 parameters in the neural net. The reward function is as simple as the further north, the better. The softer hit the ground, the better. Only two components to the reward function. Nothing about what walking looks like, nothing about what running looks like, but it invents that something like running or walking is what it should do to optimize reward. This is in the Mujoko simulator, which is built by Emil Todorov's group at University of Washington.
If you have the value function, why do you need a policy?
That's a really good question. So why do we have both a value function and a policy in this approach? So this is exact same algorithm, just a changed environment. If you try to only learn a value function, then you need a model to look ahead against that value function. So you still need to learn something else. If you learn a Q function, which encodes the value of both state and action, it's a little less clear how to do that. It's also, the tricky part with learning Q values is that you learn this value, which will dominate. So here, the reward is head height. The higher the head, the better. The Q function is this function that has very high magnitude, but what you care about is then the difference between two actions. What is the Q value for action 1 versus action 2 in a particular state? And the fact that you need to figure out the difference between the two, but you actually get mostly trained on the overall value makes it difficult to zone in on what you care about to make decisions. There might be loss functions you can define on Q functions that zone in more specifically on how they distinguish between actions, but now effectively you're almost learning a policy. And so we directly learn the policy, but then the value function is there to get better policy gradient estimates. Yes?
You mentioned it briefly here, but if you actually apply these things on a robot, how do you deal with negative reward? Right? It's important to have negative reward when you do exploration, but you don't want to break the robot.
Yeah, let me get to that a little later. That's a very important question. And I have some slides that will get to that a little bit. Let's see. Turns out this approach I just showed to you also works on Atari Games without change. So this is an approach, the trust region policy optimization approach, allows you to learn to control robots, also learns to control how to play Atari games. Wasn't the first approach to learn to play those games. It does turn out, though, that the A3C method, that is the highest performing method out of DeepMind right now, is essentially the same as TRPO plus generalized advantage estimation, but then run asynchronously over multiple machines. So even though initially a lot of the work here was with Q functions, seems like currently these policy optimization approaches are easier to get maximal performance out. Yes?
It's really cool. Part of the problem with all the reinforcement learning, I guess, is coming up with a reward. And it's easy with computer games, scores an easy one, and some simulators where you come up with a reward and go, cool. I think it's partially to do with the robotic task control with robotics. What's more reward? Like, what is it?
Yeah, great question. How to deal with a reward. You're anticipating one of my future work slides, so let's get to it there. I think it's a really important problem. One of the things we actually started thinking about, as you see, like all the different approaches, there's many more, is how to benchmark these things and how to see what does better. And so we set up a big suite of robotic control tasks, going from very simple cart pull type things to difficult things like locomotion, to even more difficult things where you need hierarchy. At least we think so, most likely. For example, this task here, top right, you're in a place where you're supposed to eat green pellets, avoid the red pellets. But actually, you need to learn locomotion to even move around in this space. And learning locomotion, you don't get rewarded for. You only get rewarded once you actually eat a green pellet. It could be that you learn locomotion, and you eat a red pellet, and you realize, oh my god, this whole thing of learning locomotion was a mistake, because I got a negative reward eating a red pellet by mistake. So this is a kind of problem that's beyond what's typically possible right now, but that's kind of the goal also, to set things up that are beyond what's possible. Then you can make a lot of these partially observable, and we're also starting to look at driving. Then we set up a wide range of algorithms and benchmarked them. The kind of quick scoop is that the algorithms that work best, these are all policy gradient style algorithms, are trust fusion policy optimization, essentially is best for all of them. Natural policy gradient, if you do some trickery that comes from trust fusion policy optimization, is pretty close on quite a few problems. And then deep deterministic policy gradients are really good on a very small set of the problems, and then don't get anywhere on the other problems. So there's something there to be investigated, because it's really, really good on the few problems where it does learn something. The code is all available in RL Labs. You can try this out yourself. The benchmark tasks we've now actually put out in something called OpenAI Gym, which you can also interface with. You can download everything to try things yourself. Of course, the question is how to learn real robot skills where you don't have as much data. Still want to learn a big neural net. If you do standard policy search, it'll take too long, especially if you have complex dynamics, complex policy to learn. Supervised learning, on the other hand, is quite feasible. If somebody gave you demonstrations, well, one way to get demonstrations is to generate them yourself through trajectory optimization methods, which are good control methods, iterative learning control methods, to get good example successes. So this is what guided policy search does. You generate successes on very specific situations where you can iterate over the same situation over and over, use supervised learning to then train a neural net that generalizes to new situations. This generalization can be well beyond just what you might think at first. You can, for example, at test time, want to only use vision, but at training time, you can work in an instrumented environment where you train the robot with access to full state. But then the neural net has to learn to mimic that with only access to images. Here's the neural net we use for that. Here are some of the tasks we've looked at, and here is some of the learning in action. So what you see here is the robot alternating between different goal locations, learning a trajectory-specific controller for each goal location, so learning about 5 different trajectory-specific controllers through ILQG. And in parallel, it's training a neural net to match each of those controllers. And in about an hour's time, this is a sped-up video, it's able to learn a task like this, where it generically is then able to put the block into its matching opening. Here are some other learned skills. So hanging a coat hanger onto a bar. Placing the block, for which you saw the training. We're now seeing the robot view. Here it has to learn to pay attention to nail and hammer. So very interesting. We don't tell it that the hammer and the nail matter. We just have trajectories that are good. It then needs to make sense of what it saw in the pixels and how that could relate to the actions that were the right actions, and has to figure out that hammer and nail are things to pay attention to. This dexterity-wise is quite difficult to get a robot to screw a cap onto a bottle. can apply the same thing to other robots. It doesn't need to be manipulation. Here is same thing for flight. This is still in simulation, but here it's train a neural net with the same approach, guided policy search, to learn to navigate these obstacles. And there's also some trickery here about safety to avoid too many collisions during training time. What are some of the big challenges ahead? I think one of them is data. And so we've seen quite a bit of work recently on how to augment the amount of data we might have available. There's the work from CMU with Baxter. It was one of the first papers to really have a very large data set. The work at Google, Peter Pastor and collaborators, where they had, I think, 14 robots set up to collect data to learn to grasp. And then there's some work, Pulkit Agarwal at Berkeley, looking at learning to poke and push objects around with the Baxter. Another big challenge, I think, is transfer. If we can address that problem, that'll go a very long way. Transfer could be between tasks, between robots, but also simulation to real world. So one of the big things that is different between simulation and real world is that in simulation you can get a lot more data. So if there's any way to transfer skills learned in simulation reliably to the real world, that will help a lot. Another big one is exploration. The task I mentioned, where the robot has to learn, in this case, four-legged locomotion, and then after that can only start collecting rewards. It turns out that with some recent work on exploration objectives, it is possible to learn to collect rewards in this kind of environment, but still a lot of work to be done to do good exploration. Rewards are tricky to come up with. For games, it's easy because the score exists. For robotics, it's always a question, what should the robot optimize? There's also a meta question there. If the robot is super, super smart and you ask it to optimize for something, it's probably not what you want after the fact because it might destroy other things that you didn't specify it shouldn't destroy along the way. The big question technically, though, right now is how to deal with really large perceptual spaces, rewards that are defined in visual space rather than state space, and how to learn those. Some recent work on that that's presented at ICML next week. There's a long way to go to actually tackle this problem. And then hierarchy, which I think is maybe the most open-ended problem, so I left the slide completely empty, but how to learn where the robot understands that there is low-level decisions like motor torques, but then there is something like reaching for an object, then there is doing something with the object, and then there is the whole day that it's planning out, the whole year it's living up, and so forth. So those are some future directions. In terms of kind of wrapping up here, there's one thing I want to throw out there, kind of a crazy thing, so don't take it too seriously. But let's look at how long Earth has been around, 4.5 billion years, and how things have evolved in that period. So initially, there was just kind of Earth. There were no humans yet, in fact, no animals either. And you can see like 3.5 billion years ago, life came about. It was just like one cell kind of organisms, then animals, and so forth. And if you look at this timeline, I think one of the interesting things to look at is evolution takes a long time to go places. And humans came about, let's say, 70 million years ago, or primates 70 million years, 6 million years ago humans, 4 million years ago walking on 2 feet, then 1 million years ago fire, and then 40,000 years ago some art. And so what's interesting to think about here is how evolution is super, super slow, which probably means that whatever brain existed back 6 million years ago, and maybe even 70 million years ago, is pretty much the same brain that exists right now. And so that whatever the brain was evolved for at the time, which was as simple as essentially collecting food, maybe building fire, whatever was able to learn to do those things, turns out that once you have a little more time on your hands because you're not so busy collecting food and so forth, you can do a lot of other things. But that ultimately maybe robotics is one of the best places to work on deep learning, for example, because if you can get robotic capabilities with deep learning, everything else might just fall out because it might be that robotics is just as hard, at least from a learning point of view, as any other problem that people have solved since. All right, some acknowledgements of my collaborators. Thank you for your attention.
Thank you, Peter. Do we have one or two questions before we go into the lunch break? Ben.
Thanks, Peter. I think the computer vision community was accelerated in deep learning through the release of some of the neural net architectures, the trained neural net architectures. And a lot of people were able to jump on board really quickly. And I think it's great that you're releasing some of that code as well. I was going to put out a request to some of the, I think you pointed to a few other groups that have resources to a lot of robots and train a lot of robots on a big data set, if they were considering releasing some of those trained architectures as well. So it's more of a comment rather than a question.
Well, maybe it's a question to Peter, first author of the Google paper.
Yes, one question over there.
Hi, Peter. I think one of the challenges for the simulation to the real world is real world model has a lot of uncertainty. You can't model in the simulation. Whilst if you deep learning, you tend to overfit to the simulation like some fixed data, which can easily be ruled by the real world.
Yeah, so interesting questions there. Overfitting, definitely something to be careful about, and of course there are a lot of tools like holdout sets and so forth to deal with that. I might actually say something in slightly the reverse direction here, is that, for example, when you run guided policy search, overfitting is almost a feature in that if you look at learning these manipulation tasks that I showed to you, learning to screw a cap onto a bottle and so forth, it turns out that if the bottle is in a particular place, you hold in the cap in a particular way, and you repeatedly get to try the same thing, and you, in some sense, overfit to that one thing, that's what allows you to get a single success. Now, of course, you need to repeat that, but the fact that the dynamics, while super complex to model contact dynamics for a cap being screwed onto a bottle, it's actually very consistent if you keep the conditions the same. And so it's the kind of fitting, it's maybe not overfitting, but fitting very, very much so to that one particular situation to master it, and then moving on to another situation, fitting very, very precisely to that situation, master it, and repeat is what allowed those kind of manipulation successes. The neural net luckily then learns how to generalize to a wider range of situations. But the initial learning, the thing that bootstraps it, is, if anything, really close to overfitting. Yes.
I saw that you mentioned driving in one of your slides. Do you want to say anything about, like, if you can say anything about what you're doing with driving and how manipulation is different or similar, or sort of things that go from one to the other?
Sure. So, yeah, it turns out that for driving, right now at Berkeley we have a big initiative with some 10 or something companies that are all kind of pooling together to form a consortium to have a lot of efforts of specifically deep learning for driving. Some of it is pure perception, things like tracking pedestrians, tracking other cars, and so forth. The angle I'm interested in is the perception and control, bringing those two together. One thing that's quite different for driving, I think, is that actually supervised learning might have a better chance in driving in the sense that there's a lot of cars out there. A lot of data can be collected. There are things to be careful about when you apply supervised learning because, for example, the covariance shift problem, which was highlighted by Drew Bagnall, Stefan Ross, and collaborators, where you actually can't just learn control straight up from optimal demonstrations. You need to then interleave your controller that you learned with more demonstrations to learn the right thing, so you learn to steer back onto things. So I think those things aren't naturally in the data that's being collected, and we need to be careful about. Reinforcement learning might be a little bit of a stretch for driving, especially if you start in the real world. But I think personally there's a very interesting problem there in terms of hierarchy. I don't know if it would directly go into the real world, but if you think in terms of like driving, there is low-level control, there is things like lane goals, then there is traffic rules, and then there's the destination you care about. And having systems that can learn to deal with all of that, I think, is a really, really interesting challenge. And I don't know if that would work with reinforcement learning, but I'm interested in seeing what's possible in this kind of multi-layer structure on the reward function.
Just a follow-up, perhaps you saw after NVIDIA released their end-to-end video, Amnon Sachua from Mobileye released a video saying you would need exponentially more training data with end-to-end versus breaking it into pieces. And so I don't know the answer. I wonder if you ever thought, if you're familiar with that sort of debate in terms of, is there an exponential reliance on training data for trying to have like more end-to-end functionality versus more well-engineered submodules sort of chained together?
So that's a good question, because end-to-end doesn't necessarily preclude well-engineered submodules, because end-to-end could have any kind of structure, and you could, as long as it's differentiable, you could train it end-to-end. So you could actually have a module that is designed more specifically for control, but that is still trained in connection with how the perceptual part is trained.
For example, if you see an unusual vehicle like a big dump truck on the road, in end-to-end you have to sort of nearly crash into the dump truck to generate a control signal that would give you, learn something perhaps, versus if you can just learn about dump trucks, then maybe later when you might crash into a dump truck, you were sort of trained about those. But Larry probably has an answer for that.
You know, I saw the comments from Mobileye, and the example was a dump truck on a highway. And in simulation, you can put the dump truck anywhere you want, and you can, in simulation, say go around it. So that was sort of red herring that was brought up. I don't see a problem of exponentially many examples. Certainly, it beats having exponentially many coders labeling the data.
So I think maybe the bigger question there to me is not so much, I'm not sure if you need more or less examples. Certainly, the more prior information you put into things, the less examples you need. So if you do something either structuring or training-wise, I think the reason modular could have some advantages at times in something like this is in terms of better understanding the capabilities. So you could have a decomposed evaluation of how reliable is this thing at detecting lanes, and you could actually check how good is it at doing that. You could separately evaluate how good is it at steering on into a lane, how good is it at braking with a certain braking distance that is available to it, and so forth. You could evaluate those things separately, which might be easier to then have comms in the same thing. If the thing displays to you, here is where I think the lanes are, here is where I think I should be going, rather than the thing just pushes the brake, gas, and turns the steering wheel without displaying any internal information about what's going on, it might be less comfortable until it's actually been successful for a really long time and you might not care anymore. But at least for the initial stretch, it seems transparency of what it's thinking could make it more comfortable to actually try it out. I don't think it has to crash into dump trucks, by the way, to learn about that. That would be, there's a lot of ways around that. So you could, if it was supervised training, you're avoiding the dump trucks, so it's already being trained to avoid them. If it's reinforcement learning, you can imagine a reward function that's a little more shaped. That's not just like, do I reach the destination or did I not reach the destination, but that also incorporates distance to obstacles that you might have from a laser and so forth. And so in that sense, it might learn more quickly than you might think.
All right, thank you very much, Peter. I hope you all enjoyed the morning session of our workshop. We will be back here at 2 for more invited talks and the poster presentations and, of course, the panel discussion in the end. See you all back here at 2. Thank you.